Start from A, get an output in B, but then I know this can be also fed into the second machine, G, okay? So that gives me the output, G, right? So this composite is usually written as GF, and what does it do? G composed F, if you take an X, it first evaluates Fx and then evaluates Z. Okay?
Also, it first evaluates f of x.
Yes.
Then G.
Yes. Yeah. So that's why I draw this diagram.
So then just to be sure.
Yes, you have to be sure.
The pattern of
The pattern is very, very important. So G composed F may not, the other one may not exist. There's a question also to show that. So the other one may not exist even, right? So yes, that's very, very important. And there are a few other things. There is a very natural function from any set A. I write it as 1A. What does it do? It takes an input of X and doesn't do anything to it. It just outputs that same thing. Okay? It is called the identity function. There's another one which is very, very similar. Suppose if you take a subset S, then there is a function from S to A which I usually write as iota of S. It takes a member and also does nothing. But these two are different. This is called the inclusion of S in A. It is not the same unless S is A itself. Okay? So if S is not equal to A, then the inclusion of S is not equal to 1A because of the simple fact that domains do not agree. Yeah? The rules agree. So often the rule, given input, what happens to the output might be same. But you see, I also find this difficult to believe because rule is not what? The law of the land is not what happens to you. The law of the land is what happens to you, what happens to me, what happens to him and everybody. The law of the land is not about a particular person. Right? So the rule cannot be for a particular X. So the moment when you are speaking about the rule, the domain is automatically coming in. What are the inputs, values? Right? So the domain, once it changes, the function is different. The rule is different. Yeah? So, the rule is different. Clear? Okay. Now, there are a few other things about, my time is getting, but there is another, about associativity. So if you have, it can be seen, if you have such things, so you have an F, you have a G, you have an H, okay? So I do the composites. So you have a G composed F and you have an H composed G. Okay? Alright? So now you have another level of composites, which is H composed And you have another composite, which is H composed G composed F. Right? And in fact, it turns out that both are same. So this is called the associativity law for composition. And the reason is pretty simple. You start off with something from A, input it, so it goes to H of G of F of X. That's it. Right? That's right. So this is just simple, and this is often called the associativity law. And then I'm coming towards the last exercise, which is about some more special functions, and which will be immediately required in the next lecture, is about binary operations. Okay? So, what is a binary operation? It's a very special kind of a function. See, dear things get to be named. Okay? In algebra, we will be seeing this is getting to be very, very close to us, and hence we name it. What is a binary operation on a set X? What is it? It's nothing else but it's a function from whose domain is the set of pairs and the codomain is X. Okay? So we often write this as like this. We often also sometimes we often write this like this. So here is this X and here is this. So in the vertically we put the first coordinates, horizontally we put the second coordinate, and this is my X star Y. Okay? So you often call this multiplication table. Okay? Remember your usual multiplication table. Multiplication is a binary operation. Addition is a binary operation. Subtraction is a binary operation. Okay? Division is not. But not on the whole of reals. Okay, I leave it to you to say why. And so there are several binary operations which we will be looking into. I have given some things, when it is said to be associative, when it is commutative, when it is said to have an identity. Especially do that last example before next week. Okay, so that will be needed next week. All right. Yeah, I'll stop. Okay, remember our sessions have been gracefully extended by the university to 3 hours. Okay, not 2 hours. Now, the first day, it's fine, it's the first lecture, but from next, so how we will utilize these 2 hours? So let's say we meet for 1 hour 50 minutes, okay? So, and take a 10-minute break, and then for the last hour, it will be question and answer session. So it is for you to come up with problems, doubts, questions, queries, okay? I would invite questions up to that point. If I'm on lecture N, that means about self-assessment N, up to N, starting from 0 up to N. Okay? I would not invite questions from N plus 1 in the nth lecture. Yeah, it will be in the next lecture. Yes. Okay. All right? Yeah.
So does it mean next week's lecture is about vector spaces?
Yes. So the next week's lecture will be about vector spaces, examples, how to construct more and more examples, okay, and how to see them. The more important thing, you see, the whole idea is that when do I say memorizing? I do not say that memorizing is not a way of learning. When you have understood, it is also some kind of memorizing, yes, but there is a difference between rote learning and memorizing. What is it? If you have understood it, rote learning and understanding, if you have understood it, forget about the context. You go somewhere else and you see something and it strikes, aha, this is this. Okay? The fact that, aha, this is this, means that you understood that concept. If you did not, until and unless I give you that particular context of that, reproducing that concept, you will not be able to do. Right? So that's what I expect. So you should be able to understand these concepts, which are very simple. Very, very simple. Okay, for instance, 2 days back, one of the teachers who was also doing this, he asked me that, well, all of this is so abstract, it is not at all necessary for, he is a school teacher for him. I said, no, it is not. It is a very, very important thing to know. For instance, what will you tell a young child if he says, what's a lie? And then after all his explanations, I said, okay, if suppose I was the child and I draw this as a line, would you accept? He said, no, I'll give 0. I said, why? All the explanations that you have given doesn't exclude this. But I know what you are meaning by it. I know that you wanted to say something like this. But you didn't exclude this. Then how would you exclude this? Well, he couldn't answer. But here is a very, very simple answer. You take any line, cutting it, and take an orthogonal line, and take another such. I know that these two triangles are similar. So, the ratio of this by this are same. But if you try the same thing here, it will fail. Okay? It's going to fail. So here is something which is a strange property. Okay? So I look, if that child doesn't know how to know similarity, I just tell him, don't take any two things. Compare. Take the ratios. What do you see? You say they're same. They're the same over there. They're not. So do you now see there's an intrinsic property which differentiates this from this. Now let's come back. What is this? This is exactly saying that this one, if this was my origin, this point was my origin, this black line is a subspace. Or what? It's exactly that what I'm saying. Okay? So what we are learning here It is very, very relevant even for very, very childish geometry. It's actually a very, very childish geometry. For a child's geometry, I mean to say child's geometry, for Euclidean geometry. Okay? There are many evolved versions of this, but that's much later. That comes on much later. But this linear algebra is a very, very beautiful thing to learn because it even enlightens a young child. Okay? The message from here enlightens. So it is going to be useful even in your teaching if there are any teachers here. Yeah? Okay, so I'll stop here. Yeah.
Hello, sir.
Hello, can you hear me?
Yes, I can.
Yes.
The section on index families, so we're not covering it.
Yes, I didn't cover it today. I will need it later on.
Okay.
And when I need it, I will come back to it.
No problem.
And there is another thing which I believe I would also be requiring, and I'll come back to that later on again. It would be some elementary knowledge about complex numbers.
Okay.
Yes,
Yes, it is a little bit that I'll require.
yeah.
And the only thing that I'll require is complex numbers are things like a plus ib and so on, where I squared is minus 1. And you should know what is the argument and what is blah, 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 the conjugate and so on. But much more, a fact, well, this was one of the fundamental theorems. There are several proofs of this, all beyond the level of this course. So we'll not prove it, but we'll accept that fact. And that fact is, if we have a polynomial with complex coefficients, it has a root. Okay? This has immense application in understanding the notion of an eigenvalue and eigenvector. And it is only at that stage that I will require my complex numbers to become as scalars. For the rest of the course, we will be dealing with real vector spaces, except for that little part, which actually is not, there are two ways to look into this. Firstly, to get you acquainted with vector spaces with real numbers, and then try to persuade you, saying that, well, you see, we didn't quite use anything special about real numbers here. We only used the fact that we could add two scalars uniquely, we could subtract, we have a zero, we can divide, right? Nothing else was required till that point. Well, when you once agree to this, then the next step would be, then why don't I take complex numbers now as scalars? Everything that we have done up to this will hold good. But then we will see something where complex vector spaces and real vector spaces differ, and the picture of eigenvalues and eigenvectors become much more clear and beautiful in complex vector spaces, and it becomes, we'll see that, it becomes a little bit tricky and well, we have to be careful. It cannot be that simple with real vector spaces. So after that, we'll again come back to real vector spaces. Yeah.
In general, we have a Telegram group. Telegram, that is a people of WhatsApp.
Okay. Okay.
And the biggest complaint that has come up for the guys is basically that the textbook is useless. I kind of disagree, because I did a course, I failed, and I think I know why I failed. Because from what I picked up, I think you are more focused on us understanding concepts And it looks like the best way to understand concepts is the ability to do proofs. Am I right to say that?
Yes, correct. Correct. The best way to understand concepts is the ability to do proofs, 1 and 2, to use them in applications. Now, theorems and proofs. Theorems didn't come in a day. They came after a long experience of repeated usage of that. And then suddenly someone sees and says, oh, well, why are we using this? If we have A, B, C, D, then we can immediately see that E follows. That becomes a theorem. Okay? But people have been only doing that. So they have been computing. So several years of computing experience has given rise to theorems. So theorems are actually ways to cut your computation down. And even today, when we have so strong computational facilities, it is becoming, computation is itself getting questioned in the sense that, and therefore this understanding is coming up, that you should avoid computations till the time you cannot any further avoid it. So then, what do you do during this time? You simplify. And then how do you simplify? So develop a theory, develop a structure, which tells you how to simplify things and come up with the simplest possible thing and then compute. Right? For instance, I don't like in which many textbooks use determinants right and left. Determinants are a very nice object, but they shouldn't be used right and left because, firstly, they are difficult. Secondly, they're computationally also difficult. No one, even today, none of these machines, right today, from the 60s, nobody developed a computer algorithm to compute the determinant of a matrix using the usual Laplace transform kind of it, Laplace reduction kind of it. The whole reason is, for a 10-order determinant, you have to find 9 Laplace, 9 orders. And then, for each one of them, you have to find 8 orders. So it goes down to factorial 10 automatically. So it's huge. Nobody does. On the other hand, how do people compute the determinant? Well, the determinant is a product of eigenvalues. 1. It's a computation, right? It is bad. It doesn't tell us many things about it, but it's a computation. So theoretically, what's the determinant? It's something called a multilinear form, which has some permutation, satisfies some kind of laws. Okay. So it is, when we study such things as multilinear forms, determinants come out to be very, very important. But not here, and you can completely avoid the whole notion of a determinant in this course. So, and the way to do it, that's how I said I will be requiring complex numbers. Okay? And so theorems shouldn't be taken as an impediment to understanding. Okay? But they are more of a way to suggest, this is not the right way, this is a shorter and a better way to compute. Okay? And you will see, once you have developed this, you will immediately see very easy ways to look into things. So that's the whole idea. Yeah. Yes, the textbook. Well, now we are coming to something very mundane and very, very involved also. People have bought this textbook and it's quite heavy, quite expensive. And the first year, second year, a little bit of third year. So I cannot change the textbook just like this. Just because I don't like it. On the other hand,
You recommended a book.
I recommended Axler's book. Yeah. I recommended that book. And what I did was, I produced these self-assessments questions. You're not expected to submit, but definitely you're welcome to discuss, send in questions and so on. Now, what does the self-assessments do? When we were young, there was a very, very common practice with Russian textbooks. Some of them were not actually textbooks. They would just give the definition and the notation and definition and start off with problems. Okay? So when you develop those problems yourself, you'll have written for yourself the textbook. Okay? So there is a much better way of learning. That's via developing those problems. Okay? So I tried to do something similar with the self-assessment questions. Yeah? So that was the intention. And obviously the other thing that I tried to put up was these lectures so that we can meet and have discussion and have our problems ironed out.
Ideally, when we come here and say next time, surely we should say we did this and I don't understand.
Yes. Okay. So first 2 hours would be our, whichever permutation you might suggest, we might take the first hour and then the first 2 hours, or first 2 hours of lecture and then 1 hour of questions. Okay. Okay, good. That would be fine. Okay. Cool. Thank you so much. Thank you.